Cool. And the AI companion is still on. Beautiful. Well, happy Monday morning, everyone. I'm just getting back from a week off skiing in the mountains, ski bum. So it's fun. Sorry, I just got an AI notification again. As far as overall announcements for me, I just want to remind people about sharing the news, spreading the PyHC gospel, if you will, on the summer school that's happening May 20 to 24. We also were awarded about 50K of NSF funding for travel support for students wanting to attend. We put out a blog post about that, the information about it, and applications to receive that are also up on the Summer School 2024 page. So please be sharing that with everyone and just, remind people to be signing up. Even, just with this first wave of advertising we've done, we already have around like 170 people signed up or so. So that's pretty nice. And my other reminder is that our spring meeting is coming up in just about a month or so. So if you haven't yet, please remember to register for that. I'll be sending links to remind everyone of where to go to see all this information in the follow-up email for today's telecom, but there you go. Sean, do you have anything as the tech lead?
Yeah, I can add that at the summer school, we're making good progress planning a fun coding challenge game for the students that will be new from last year, and it'll involve like some fun prizes like Amazon gift cards or ChatGPT subscriptions, and it'll be very informative. So that's been an exciting effort. And I can also say that FEP1 is getting pretty close to being in the state to where we will vote on it. Uh, John has done some very good work updating the language, especially around the immutability issue, which had been holding us up for a long time. So we plan to hold the first formal vote on that at the spring meeting. So I encourage people who have been following along that discussion to check out the pull request on GitHub. Yep, and that's all I got.
Wonderful. And the more discussion we get early on, the more refined it'll be by the time we get to the meeting. So please take a look at that, everyone, myself included. All right, let's go ahead and get started with the main event of today. We have Chung Jae-woon here to talk about his magnetosheath model. Go ahead and take it away.
Thank you. Let me share my screen. Do you see my screen?
Yes.
Yes, you do.
Okay, cool. Yeah, hi everyone, nice to meet you all. I'm Jae Jung, and I present about the development of a user-friendly magnetosheath model, which we named MC-SPY 23. So it's based on Python, so it's at PY, and 23 is it was released 2023. And oh, okay, so this is just contents. So among the interaction between the solar wind and the Earth, highly charged solar wind ions like O8 plus or O7 plus can do the charge exchange with the neutral atoms around the Earth's atmosphere, actually outer atmosphere called exosphere. And so these neutral atoms are mostly hydrogen. And after the charge exchange, they emit the soft X-ray, which is X-ray in the lower energy band. And this magnetosheath between the magnetopause and bow shock is the strong soft X-ray emission region due to high abundance of the solar wind ions and also exospheric neutrons. Several spacecraft missions, including REXI, Lunar Environment Heliospheric X-ray Imager, and SMILE, Solar Wind Magnetosphere Ionosphere Link Explorer, will image the side plasma structure because they have soft X-ray image on board. And this right figure illustrates how this magnetosheath or cusp structure can be seen utilizing this kind of X-ray imager on the spacecraft. And by the way, this SMILE mission name is kind of named so because this magnetosheath and cusp structure kind of looks like smiling face. And to calculate this soft X-ray emission, it would be helpful to have magnetosheath model, simpler than the MHD simulation, so it helps to predict the soft X-ray image and analyze the REXI and SMILE data. Before we go into the model itself, I'll explain the coordinate system we adopted. So first, we used the aberrated GSE coordinates to account for the Earth's orbital motion. And because this magnetosheath is continuously moving, Cartesian coordinates is not appropriate to study the structure. So we use the normalized distance f. It is the distance between the point of interest in the mate pose in radial direction divided by distance between the bow shaft and the mate pose. So basically, f this f equals 0 means that point is at the mate pose, and f equals 1 means that point is at the bow shaft. And we used two angles, latitude and longitude, to denote the point in the 3D matrices. So this is our model concept. User inputs the position in the matrices and message highlighted for convenience, and throwing the IMF conditions in GSC coordinates at that time. And user select the boundary of the matrices. Currently, we support the Hsu mate pose model and Yerlinek or Yera-Baoxiang model. And after the boundaries are selected, model calculate the plasma parameters in the matrices, and we have 4 modules to calculate these parameters, which is MC by MHD, MC by Sprater, MC by RV, MC by SC. These 3 models are explained later. They are just the implementation of previous models, and this MC by MHD, which is based on OpenGCM MHD simulation, is what is developed in this project. So it can provide number density and plasma velocity, temperature, and magnetic field in the matrices. Now, if the option that was basic about our model, and if optionally user input the X-ray telescope position and look direction and field of view, our model has another module which is called MC by X-ray, which can simulate the X-ray emission rate viewed from the spacecraft. Now I'll first explain our MC by MHD module, and it was based on the OpenGCM MHD model to generate seed data for the seed data, and the SEMIS data was to use to validate our model result. We simulated 14 different MHD input conditions. 2 IMF BZ conditions were simulated, plus minus 4 nanotesla, and 7 different surround plasma density conditions were simulated, 1 to 30 per cubic centimeter. So 2 and 7, it makes 14. And other surround IMF parameters were set to constant, like this. Bx and By was set to 2 nanotesla, Vx velocity was set to 400 kilometers per second into the or GSX direction, and temperature set to the 10 to the 5th Kelvin. And note that only 2 IMF conditions were tested, and though we are planning to test more, and velocity and temperature variation is not included in our current version. Now, after we ran the MHD simulations, we constructed a framework of the module. So for each surround IMF conditions, we first defined the mate pose and the bow shaft positions using density gradients. This right figure shows one example of the MHD result. This is GSC XY plane, and the color is the plasma density. You can see easily that this matrix region is easily discernible. So by calculating density gradient along this radial direction, we can define the magnetic pose and the bow shaft. So magnetic poles are drawn in the blue line, and bow shaft is drawn in the orange line. And we only consider the dayside magnetic poles for dayside matrices for this version. Now we have boundaries. We set up the matrices model grid f zeta phi with a spatial resolution of 0.1 in f, which means radially 10 steps, and 1 degree in zeta and phi. Finally, we read the matrices parameters at every grid to construct our module framework. Now, back to this flow chart. User input was converted to the coordinates in this matrices coordinates. Then we just interpolate the plasma parameters from our seed grid framework. That's how our MC by MHD was constructed. And this advantage of this module compared to other previous model is that it is based on OpenGCM, so it provides self-consistently solved matrices parameters, including density, velocity, temperature, and magnetic field. Next, we compare the model and data, the SEMIS data with the model prediction. So we compared the SEMIS data from 2007 to 2014, and its data was matched to 20 minutes average of the omni-surround IMF conditions before the data measurement time. Then SEMIS data has been classified along 6 different surround density ranges and 2 different IMF PZ ranges, similar to how we set up the OpenGCM simulation, but not classified with the other surround conditions. In contrast with how we set up the OpenGCM simulation, where we just set the constant like temperature, Px, Py, and these things. And latitude was set to 0 because SEMIS satellite has 7 near equatorial orbit. Now we calculate the weighted Pearson correlation coefficient RW between observed magnitude parameter from SEMIS and predicted parameter from the MCSPI MHD. So this weight was on the data points in the SEMIS for each grid, which is the radial and the angular bin. So this RW is plotted here as calculated here for magnetic field magnitude, plasma density, temperature, and speed for northward IMF and southward IMF. So you can see that the number is quite high for magnetic field and relatively high for magnetic field, plasma density, and the speed between the MCSPI and TEMIS data. The correlation is high, but temperature shows a low correlation coefficient, which is kind of expected because TEMIS data are not binned by surround temperature, and thus including all the MHC data from various surround temperature. Also, like the surround temperature average from this compiled paper was like such a 3 times 10 to the 4th Kelvin, but for the MHD simulation, we used 10 to the 5th Kelvin, so it was a bit high. So we are trying to correct it in the future version. Next, we made a suite of magnetic models that includes modules which employs models in previous literature, so users can choose the model of their interests. So following modules are included: MCSPI Sprater, which is based on Sprater 2066, and MCSPI-SC based on Sutseg and Escobar 2012, and MCSPI-RB based on Romashets and Bandas 2020. I briefly explain its models. Sprater error is the popular gas dynamic matrix model, which can provide plasma density, temperature, and speed. And the Sutseg and Escobar is the model for plasma velocity. And the Romashets and Bandas is the model for magnetic field. It's an alerting model. So we implemented this model as each model as a module in our model, so user can use other models if they want. Now this is the case study to compare each module's prediction with the measurement. We do 2 case study and 1 is shown here. So left for this event, we saw the event at 2003, May 4th, and this event was used for subtext ray study. Left figure shows the GSCXY plane and GSCXZ plane. And at the center is the Earth, and magnetic pulse is drawn as the red line, and the Belgium is drawn as the yellow line. It does start at the end of the time interval. And this blue line is the cluster orbit, and it started from the orange line. So you can see that the cluster was in the magnetosphere region, but it passed the magnetosheath and went out to the solar wind. And while it was moving in the space, it recorded plasma parameters. Sorry for the noise. Plasma parameters are magnetic field, Px, Py, Pz, and magnitude, and velocity, Px, Py, Pz, and magnitude, and number density and temperature. And while it was moving through the matrices in this gray shaded area, we calculated the prediction of the each modules by using the solar wind and IMF condition at that time. So first observation is plotted as blue red, and MCSPI MHD is plotted as the green line, and MCSPI RB, which predict the magnetic field, is plotted as blue line, and MCSPI SC, which predict the velocity, is plotted as red line, and MCSPI Sprater is plotted as the purple line. So you can see that MCSPI MHD performs as good as other modules and provides self-consistent calculation of MCS parameters because it's based on the MHD simulation. To showcase the one potential use of our model, we generated ideas of X-ray images simulated using MC-SPY-MHD taken from virtual spacecraft 30 Earth radii away. So this left panel shows the side view of the Earth's matrices. So it's kind of the XZ plane view from the starry Earth radii GSE x-axis. And the right panel shows the polar view. So it's kind of XY plane. And you may expect the cusp structure in the side view, but the cusps are not introduced in our model, so there is no cusp yet. And if this is surrounding diode condition is set, IMF was set to north southward, and number density was set to 10, surrounding velocity is 400 km per second, and exposure time was set to 5 minutes. And we converted this idea's X-ray image to a realistic image, which accounts for instrument response, background, and random noise using SMILE's of X-ray simulate code developed by University of Leicester team. So left one is the same image you saw before, the idea subtext emission image from the matrices, and right one is the converted image to the realistic one, including all the noise and background. So you can see where in the ideal image, the matrix structure are clearly seen. In the realistic image, it's not as clear as before, but we expect we can still track the magnetic pulse motion, which can help the studying the day-side reconnection pattern. That was about our model. And this module can be installed and used with Python. I uploaded this to PyPI, so you can just pip install MC-SPY. And not only image-based model result is included, but also we include other modules. You can use other modules result. And the GitHub repository link is here, and also documentation link is here, which is also in the GitHub link. And currently this X-ray module is not included in the public version, but I'm trying to add it. And also spacecraft I only uploaded the cluster support, but the other spacecraft support I can add. And I'm also trying to add this to PyHC project, but I have not trained in the coding custom, so it's a bit difficult for me to understand the PyHC guidelines. So I'm having a bit of issue there, but if I give an opportunity, I can do that. So to summarize, we introduced the suite of matrices model using MHD-based gas dynamic and unearthing models. MHD-based model, MC-SPY-MHD, shows a high correlation with the damage statistical data for density, speed, and magnetic field magnitude. In the case study, performance of the MC-SPY-MHD was on par with other models, and yes, it's self-consistent. And this model can be used to provide a quick snapshot of expected soft X-ray from charge exchange from virtual spacecraft, so it can help the selection SMILE mission planning. Thank you.
Thanks,
Thank
Jason. I did see that there was a question in the chat already for you.
Let me
Becca?
see.
That's just me. Let other people talk.
I can chime in real quick, and I can mention I had heard just toward the end you had sprinkled in that you were looking at the guidelines for PyHC, and some of it was not immediately obvious to you. So I would be happy to answer any questions if you wanted to reach out to me with any of those.
Oh, great. Yeah, I'll ask some questions to you.
Yeah. If you want to do email or Slack, I'm fine with either. I don't know if you're in our Slack yet or if you have my email, but I could set you up with one or the other or both.
Oh, sure. Yeah, I first get email. Yeah. Do you know my email address? Yeah.
Yeah, I know yours, of course, but I'll just put my personal one here in the chat real quick.
Oh, cool.
Sean.polson@lasp.colorado.edu. Yep, I'm always happy to help with PyHC package stuff.
Thank you.
Of course.
Yeah, and if I remember you mentioning that things like packaging and so forth,
Yeah.
you weren't sure how to proceed with that. If talking with Sean, you find that you still need a little more help or not, I encourage you to join our Slack channel so that these developers who are doing this on a daily basis and working with all these things can also help out.
Okay, cool. Yeah, can you give me the link?
Yeah, I'll invite you to the Slack.
Oh, sure. Okay.
But cool. Thanks, Sean. Let's see, does anyone else have a question for June before we go on to Rebecca's?
Actually had a question about the emission modeling that you're doing. So you're predicting like the soft X-ray emission that's resulting from this particular like distribution of temperature and density, is that right?
Yes, yes.
And so what is I guess it's two questions, like what's the dominant like mechanism that's producing this soft X-ray emission? And then how are you modeling that?
So dominant mechanism is the charge exchange between highly charged surrounding ions like the oxygen and nitrogen and the sulfur and things like that. And also between the mostly exosphere neutral, which is mostly like 99% hydrogen in the around this exosphere. And I mean it's very difficult to model each ion's density and calculated emission rate. So usually because they are not measured, only ACE spacecraft can measure this ion abundance, but they are this highly charged ion abundance, but it's not very accurate. It's I think the consensus. So we kind of use like mesh the reaction rate between by using just ion density, just proton density, we just use to mesh the reaction rate, assuming some ratio between the proton to the each ion. That's how we calculate the emission rate. And
Okay.
for the number density, exospheric density, we just use simple model, which is spherically symmetric and the proportional to the radial cube, 1/cube of the radial distance.
Okay.
But
Okay.
it's
So
more
you're not using like some sort of database for the data related to the oxygen and sulfur and etc. to do
Yeah,
this.
it's kind of difficult to use the data-driven modeling for this. Yeah, so storage charge exchange. That's my understanding.
Oh, okay. Okay. Thanks.
Thank you.
Any other questions? Okay, Rebecca, go ahead with your question that was in the chat.
Thanks. So, hey, great presentation. This is actually something I did some research related to it on, but I'll hold my science questions, I guess, for another time. So software kinds of things. So you said your package requires aberrated GSE coordinates. Does it?
User can just input the GS coordinates and then we do the aberration. We accounting the aberration in the model itself. We have model accounted for itself.
Got it. Got it. That helps.
Mhm.
Another thing is I'm looking through your documentation and I see these RST files. Is it possible for you to create a notebook demonstrating the workflow, how to
You
use
mean
the
the
package
Jupyter
all in one?
notebook?
Yeah.
Yeah, I know Jupyter notebook, but I'm not actually actively using the Jupyter notebook, but I'll try, yes.
Yeah, that would be great because then people could just open the notebook and know how and see how to use it from step one all the way through the end and maybe see example plots like you have in your presentation. That would be great.
Yeah, thank you. I started Python like I don't know many years ago, and at the time I just used comment-based Python 9, and recently I'm just realizing many people are using the Jupyter-based Python, so that's a bit yeah.
Yeah, I get
easy
it. I
for me,
mean,
but
my transition was similar. One more comment. I'm looking. I found your paper and then I found your link to the GitHub. So thanks for putting that in your paper. That was very useful. But one thing that I see here is that you have some data files in the modeling
oh yeah, there
directory.
should be. Oh yeah, I may have not mentioned the documentation, but it should be downloaded manually from the GitHub link.
Right, but the files are in the .npy, and those aren't going to be very usable after a couple of updates to NumPy. So it'll be a lot easier for people to use them if you put them, say, in a netcdf or HDF format.
Yeah, I think about it. Yes, that's for
Yeah,
sure.
Yeah, definitely better practice to avoid those data dump file formats because they're very problematic after a few updates.
Okay, I didn't know
Yeah,
that.
I'm interested in using this package for other purposes and happy to email you about that. Email
Okay,
you and
sure,
Connor.
thank you.
That would be great. Thank you.
Some let's see. I saw John Niehoff posted a comment in the chat. GPText makes it really easy to take a commented Python script and make it a notebook. And there's a link on Read the Docs there.
Oh, okay, thank you. Yeah, I read the
Yeah,
link.
I'm constantly beating the drum for GPText because it lets you do all the nice notebooky stuff in an actual text format instead of a black box binary. So it's very cool.
Oh, thank you.
Cool. Are there any other questions for June while we're here?
I have one more question. So you
Okay.
said that you use the OpenGGCM ImageD model data as
Mhm.
training for your model. How easy is it to plug in other model outputs into your package, or does it expect some sort of special format that that particular model generates?
I think it would be not difficult. I haven't did that with other MHD model like the bachelor's or the other, but I think as long as I can give them the data and the code to extract the plasma parameter it's grid, like it's grid, and it would be not difficult to do the construct our model based on other MHD model.
Okay. So maybe that's a second notebook you could use. You could
Yeah.
create. That might take a little more work though.
Yeah, lots of notebooks to make.
Okay, thanks.
Thank you.
All right. Any further questions? Okay. Well, I'd like to thank you, June, for coming and speaking on this telecon about the magnetosheet model you're working on. And we're looking forward to hearing more in terms of getting it integrated into PyHC.
Thank you for inviting me. And yeah, I would learn many things about this Python Jupyter notebook and from your groups. Thank you.
Wonderful. I don't have any closing messages. I don't know if any came up for you, Sean, while the telecon's going on.
Can't think of any, not this time.
Cool. All right, well, let's go ahead and wrap y'all. See you again in a couple weeks' time. I forget exact topic off the top of my head for that particular telecom, but I'll of course announce it before and we'll all be mentally prepared. So thank you.
Thanks, Julie. Bye.
Thank you.